Carey Institute. It's gratifying to see such a large turnout here a midsummer night. There's still some people left in town. And certainly it's gratifying to see so many of our elderly Full Society members to be able to join us tonight. Tonight we have a very special treat in Michael Mann, who's come to speak to us about climate change, dire predictions, understanding global warming, native of Amherst, Mass. Michael grew up as a faculty offspring there, and then went out to Berkeley, where he got his undergraduate degree, returned to the East Coast and got numerous degrees, including his PhD at Yale. Then had the luck, actually, to get a postdoctoral fellowship in his hometown in Amherst and spent several years back there, where he did some of his most famous and well-known work, which was to produce what has been known as the hockey stick graph, reconstructing temperatures back for 1,000 years from tree rings. Was lured away from UMass Amherst. That must have been tough to leave your hometown to go to the University of Virginia, which is where I first met him a few years ago, and we had a wonderful visit down there. And then was lured away from UVA to go to Penn State, where he heralds now, and he has a bunch of titles there now. Michael has been in the thick of climate change controversy, always holding a white flag of the pure science behind this, but has certainly suffered his share of how do I want to put it, poking by climate deniers and the like, and has some experiences that I think he will relay to us tonight about what that is like and the entire field of climate change and where we stand. Without further ado, Mike Mann, great to have you here.
Thanks for that kind introduction, Bill. My mic, no. Shut that. There we go. Okay. Okay, well, thanks for coming out tonight. I am going to talk about the topic of climate change and some of my interesting experiences in talking about the underlying science and the impacts that climate change may have on our future. I'll start out by reviewing, the climate change basics. What's the basic science that tells us that this is not an elaborate hoax, as some would have you believe, that in fact climate change is a very real phenomenon that's taking place. So let me start out by talking about where the science currently stands. This is a statement from the most recent report of the Intergovernmental Panel on Climate Change. It came out in 2007. This is a consensus report of thousands of the world's leading scientists studying Earth's climate, and as such, it is by design generally a very conservative assessment of the science. And yet, in the most recent assessment, the IPCC came to the conclusion that most of the observed increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations. That's about as close as you'll ever see a group of several thousand scientists coming to saying this problem is very real, and indeed, as the report goes on to demonstrate, it's something that we need to contend with. And so over the course of my presentation, I'll try to give you a sense both of the underlying scientific evidence about the reality of this problem and the evidence that this is in fact something that we need to contend with, not in the distant future, but now if we are to avert the most dire, to borrow that term from the title, consequences of ongoing human-caused climate change. So what is the basic evidence, despite what you may have heard from your cantankerous cousin, or the greenhouse effect is not something new and controversial. We've known about this for nearly 2 centuries. Some of the great early 19th century scientists like Joseph Fourier understood the existence of this effect. In fact, I sometimes joke with my colleagues in evolutionary biology who contend with similar controversies with regard to evolution and the challenges against evolution, that our science is actually older than theirs. It goes back farther back than the science of evolution. So we've known about the greenhouse effect for some time, and mostly over the past 2 centuries we have been refining our understanding of the quantitative impact of this greenhouse effect. So what is it? Well, it's not this. Sorry to disappoint those of you who thought you understood the greenhouse effect. It doesn't actually work quite like a greenhouse does, although the analogy holds in some very general sense. The way what we think of as the greenhouse effect in the atmosphere works is a little bit more complicated. It's not like the glass boundaries that allow incoming radiation into a greenhouse and block heat currents from taking that warmth outside of the walls of the greenhouse. That's a little different from that. But as I said, there is an analogy. The Earth allows in solar radiation. Ultimately, it's the warmth of the sun which warms the Earth. Now, in the absence of anything else, the Earth would continue to warm up and get hotter and hotter and hotter over time if all that were happening was the sun was heating us and nothing else was happening. But there is something else happening. To come to some sort of equilibrium, the Earth needs to produce its own outgoing radiation. This is invisible radiation that we call infrared radiation. You think of as heat. And the Earth produces a certain amount of this radiation. It tries to send that off to space to come into balance with the heating from the sun. And it turns out the amount of that radiation that the Earth can produce is a function of the temperature of the Earth itself. So the Earth needs to reach some temperature warm enough that it will produce enough of this outgoing radiation that it comes into balance with the solar radiation it's receiving from the sun. Now, what greenhouse gases do is they impede the Earth in its attempt to do this. They absorb some of this outgoing radiation, and they send it back in all directions. That means some of it they send out to space. So what does the Earth need to do? It needs to produce even more radiation so that even after accounting for the amount of radiation that's sent back towards the surface, it's still producing enough, it's sending enough out to space. And how does it do that? How does it produce more of this radiation? By warming up. That's the greenhouse effect. Now, again, the greenhouse effect in reality is not controversial. There's a natural greenhouse effect due to trace gases like CO2 and methane that exist naturally in our atmosphere, and also water vapor. Water vapor in the atmosphere is a greenhouse gas. These greenhouse gases, as we just saw, warm the surface of the Earth. If it were not for the existence of this natural greenhouse effect, the Earth would be a frozen planet and probably wouldn't have life, at least in the sense that we know it. So if, again, you have a cantankerous cousin or uncle who tells you they don't believe the greenhouse effect because they heard on talk radio that it doesn't exist, you can tell them, well, then how do they explain the fact that we're here and that the Earth is not a frozen planet? Okay, so the greenhouse effect is not controversial. Now, what is more controversial, not scientifically as it turns out, but perhaps politically, is the so-called anthropogenic greenhouse effect. The fact that we are increasing the greenhouse effect above its natural level by human activities, the burning of fossil fuels in particular, but also agricultural practices that produce methane. We already saw methane as a greenhouse gas. And even old leaky refrigerators that release freons into the atmosphere. Freons are themselves also greenhouse gases. So we are elevating the greenhouse effect largely through this activity here, fossil fuel burning. Now, why is it a problem? Well, if it were only for what I've already described to you, the physics and chemistry that I've already described to you, the greenhouse effect, the anthropogenic greenhouse effect, the increase in the greenhouse effect due to our activities would probably be relatively moderate. Were we to double greenhouse gas concentrations relative to pre-industrial levels, and we're not there yet, current rates of emissions will be there in about 4 decades, we would only get a little more than 1 degree Celsius warming. That would hardly be catastrophic if we look at what the impacts of that sort of warming would have on the environment. But that's not all there is to it, because when we warm up the surface of the Earth because of this increase in the greenhouse effect, other things kick in, what we call feedbacks. One of them is that, remember, water vapor is a very important greenhouse gas, but it turns out water vapor, we can't just add water vapor to the atmosphere like we can add CO2 or methane to the atmosphere, which we do through fossil fuel burning or other practices. The amount of water vapor in the atmosphere is actually controlled by the temperature of the atmosphere itself. That means the only way you increase water vapor in the atmosphere is by warming the atmosphere. It's not what we call a forcing. It's not something that we do that impacts the climate. It's what we call a feedback. It's some internal response that can amplify the initial warming. So we warm up the atmosphere by that 1.25 degrees C that we would expect if it were only for the direct effect of increasing the CO2. That warmer atmosphere holds more water vapor. That increased water vapor, a very potent greenhouse gas, adds another 2.5 degrees Celsius to the warming. We also melt away snow and ice. Snow and ice are reflective. They reflect solar radiation back to space. If we get rid of them, or we get rid of some amount of it, that means the Earth now absorbs more of that incoming solar radiation. It's another, what we call positive feedback, just like that water vapor. It adds more warming, about 0.6 degrees warming here as we can estimate it. Finally, clouds, the biggest uncertainty in the whole equation. Clouds, we think, act as a negative feedback. That is to say, when we warm the climate through increasing greenhouse gas concentrations, our models tell us that the most likely effect is to increase the reflective property of clouds. And just like ice and snow are reflective, low clouds in particular are reflective of solar radiation, and if we have more of those low clouds, then that's a cooling effect. So if global warming leads to more low clouds, that will actually offset some of the warming. That will be a negative feedback. It'll actually cool the climate relative to what would have happened in the absence of those changes in clouds. But you see all those question marks. That is the most uncertain component, again, in this equation. Some recent research suggests that it's equally, if not more likely, that another effect may outweigh that reflective cloud effect. That when you increase high cirrus clouds in the atmosphere, these are wispy clouds, they're very high up in the atmosphere. You look at them, you can sometimes barely see them. They look almost invisible, so they don't have much of a reflective property. But it turns out that if you could see those clouds in the infrared region, as some insects and birds can see, they would no longer look wispy and thin. They would look thick. They would look like very thick clouds. Those clouds in the infrared part of the spectrum are actually very absorptive, and that means that they actually act like greenhouse gases. So there's this other possible cloud effect that could, in fact, amplify the greenhouse effect, and that would be a positive response. So we think on balance, clouds are a negative feedback, but that's highly uncertain. They might even be a positive feedback. That's how uncertain that number is. So if we take these best estimates, we add them together, it comes out to about another 1.25 C. This is a little bit out of date. If I were going to update these numbers, I would end up decreasing that negative number from clouds, and we'd be probably closer to 1.75 C here. So we'd have to add nearly 2 degrees C to that initial 1.25 degrees C, and we'd end up at something closer to 3 degrees Celsius. And that's no longer trivial. 3 degrees Celsius, that is a 5-degree warming of the global average temperature, would lead to profound changes in the global climate system, as we'll see. How do we know this is actually happening? Well, there's CO2 and other trace greenhouse gases, methane, nitrous oxide over the past 10,000 years. That's the spike due to recent human behavior on a 10,000-year time scale. We can go farther back than that, if you like. We can go to Vostok. where there's a very long ice core, and we can look at the trapped gases in those layers of ice back in time, and we can actually estimate CO2 levels in the atmosphere back hundreds of thousands of years. And you can see the ice ages coming and going. There they are. But over the course of these ice age, glacial, interglacial variations over the past several 100,000 years, CO2 never got above about 300 parts per million. Right now it's about 390 parts per million. If I were to give this talk a year from now, I would tell you it's 392 parts per million. If I were to give you this talk 2 years from now, it would be 394, maybe 395 parts per million. That's how fast those numbers are increasing. Turns out this record has actually been extended now more than 700,000 years, and nature never took CO2 levels above about 280 to 300 parts per million over that 700,000 year time frame. That's where we are now, at about 390, and that's where we're headed if we continue to engage in what we might call business as usual. If we continue on the current trajectory of fossil fuel burning, we'll be somewhere upwards of 650,000 parts per million by the end of the century. That's more than twice the pre-industrial level of about 280 parts per million. So we are changing the atmosphere's composition in a profound way. In fact, we think that CO2 levels now are probably higher than they've been something approaching 10 million years. And if we continue on that trajectory, we have to go back tens of millions of years to find CO2 levels as high as where they'll be by the end of this century. Well, how do we know that anything's actually happening as a result of that? Well, global temperatures are warming. We only have instrumental temperature records for a century and a half. And they show this warming, which has accelerated in recent decades. It's about 0.2 degrees Celsius per decade at present. That translates to a 2 degree Celsius warming, roughly a 3.5 degree Fahrenheit warming per century. That's the trajectory that we're on right now. And the instrumental measurements bear that out. The warming isn't uniform. There's more warming over land regions than over ocean regions. So it turns out that if you live on land, as most of us do, we will see more warming than the nominal number you see cited when people talk about global average temperature. Global average temperature mixes, let's go back, mixes in a lot of these ocean regions that aren't warming quite as fast as the land. And I'll come back to that. Okay, well, you might say, I heard on that same talk radio show that these global temperature measurements are completely mired in urban heat bias. They've been taking thermometer readings in bad places. The readings are compromised. We can't trust the data. So suppose you throw out the global temperature. You'd have to throw out the ocean and the land regions. To do that, well, then you can look at any number of other variables, and it turns out they tell the same story. Increasing sea level. Sea level is increasing in an internally consistent way, given the amount of warming that we're recording. The northern hemisphere snow cover is decreasing. I could show you 100 other variables, and they all tell a very internally consistent picture of a climate system that is changing more or less the way, as we'll see, the climate models tell us it ought to be changing in response to this increase in greenhouse gas concentrations. Now, you might ask, well, where did you enter into this picture? How did I get tangled up in this issue? Well, more than a decade ago, in what at the time I thought of as an entirely harmless and almost academic exercise, my co-authors and I published in the journal Nature a reconstruction of surface temperature patterns. And we saw that the thermometer measurements only go back 150 years. But we can turn to other data, we call them proxy data, like tree rings and corals and ice cores, and try to piece together the picture of how the climate changed further back in time prior to the widespread instrumental measurements that we have for the past century and a half. And my co-authors and I published these reconstructions of surface temperature patterns. What's shown here is areas that are warm relative to the 20th century average. You see in the warm colors, in areas that are cold, you see in the cold colors. So we tried to reconstruct the spatial patterns of how temperature changed in the past. We were interested in things like El Nino. How did El Nino change? You see El Ninos coming and going in the past. You see all sorts of heterogeneous patterns of warming and cooling that tell us things about the dynamics of the climate system. These were the sorts of things that we were interested in trying to learn from these paleoclimate proxy data, almost as an afterthought. In fact, in response, I believe, to one of the reviewers of our paper who said, well, that's all, very nice, but why don't you tell us something about the average temperature of the Earth? That's what we're really interested in. And so we said, well, yeah, we can do that. We can average over these patterns just like we would average over the instrumental data that we have in more recent time to come up with a single number. Seems sort of boring. You don't learn much from a single number, but we can calculate that single number, the average temperature of the northern hemisphere. We average over all this interesting variation, and we can plot that back in time. And in fact, a year later, we were able to go back even further than in our original study. We could go back 1,000 years, and that's the picture that we got. The blue is our reconstruction of surface temperature patterns over the past 1,000 years. The gray may be hard to see, but you can see there's this gray shading, which is pretty wide. That's a measure of the uncertainty, pretty wide uncertainty in our estimates of past temperatures, because after all, these aren't thermometer records. These aren't pristine measurements of temperature. These are things like tree rings and corals and ice cores, very imperfect thermometers, if you will. And so these estimates were quite uncertain, but we were able to estimate the average temperature of the northern hemisphere. The red shows the recent instrumental record. The gray is the uncertainty. And this figure, if you will, which became known as the hockey stick because of its overall shape, suggested that recent warmth was in fact anomalous over at least the last 1,000 years, as far back as we could go with these estimates, even within these gray uncertainties, which were pretty wide. This was featured prominently in the 2001 IPCC report summary for policymakers, and that means that it quickly became an icon in the climate change debate. And what happens to icons in the climate change debate is things like this. This is, you can only assume a lobbyist of some sort. I don't know exactly. I don't know the source of this cartoon, in fact, but a colleague once passed it along to me. And it shows some individual breaking the hockey stick, which is what climate change contrarians decided they need to be able to do to destroy this icon of climate change. But in the background is an interesting sort of footnote on all of this. In fact, if this lobbyist wants to break the hockey stick, he's got at least a dozen hockey sticks he's going to have to break to do it. And in fact, history has more or less reinforced that message over the more than 10 years since we first published our estimates in the late 90s. Many different teams using different methods, different statistical methods, different types of proxy data have come up with all sorts of different estimates of the average temperature of the globe, or to be more specific, the northern hemisphere, where we have much more data over, in fact, even a longer time frame than the last 1,000 years. And these estimates don't agree on a lot of the details. Some of these reconstructions have a colder Little Ice Age. Some have a warmer medieval warm period, if you will, in here. But what they all agree upon is that in no case is there any evidence of warmth over as far back as these records go, a little more than 1,300 years here, that reaches the level of warmth in the last century. So that appears to be a robust finding. That is a finding that has been reproduced in essentially every scientific peer-reviewed study of this problem since our original work in the late 1990s. And in the most recent report of the IPCC, in 2007, they actually strengthened the conclusion. They said that the recent warming is likely anomalous in as far back as at least the past 1,300 years, even a little bit farther back now, as far back as these estimates go. Okay, is there other evidence that the changes that we're seeing are unusual in a long-term context, changes in the climate? Well, there is. If we look at the record of retreat in mountain glaciers around the world, they are retreating at alarming rates that are unprecedented in many centuries. In some places, we know we can actually date the ice distribution back more than 12,000 years. We know that there has been ice on the top of Mount Kilimanjaro for at least the past 12,000 years. Of course, that ice cap was immortalized in Ernest Hemingway's Snows of Kilimanjaro. But if we plot the current retreat of that snow cap, what we find, and my good friend Lonnie Thompson here is seen standing next to a remnant of one of the ice fields on Kilimanjaro that's now disappeared. And what he'll tell you is that within the next 15 to 20 years, if he makes it that long, he could easily be standing next to a sliver that looks like this, and it would be the last sliver of ice on Kilimanjaro. So that ice has been around for more than 12,000 years. We're seeing it disappear before our eyes. At current rates of retreat, there will be nothing. There will be no permanent ice field on Mount Kilimanjaro. There will be no permanent snows of Kilimanjaro in our lifetimes. And that is a profound change in our environment that we're seeing take place before us. And this story is told many times over if you look at the retreat of mountain glaciers around the world. Arctic sea ice. This is a story that's unfolding as I'm speaking to you. In 2007, we saw a record low that was not matched in the subsequent years. Arctic sea ice reached its greatest level of retreat in late summer than we had ever seen. Nearly only about 3 million square kilometers of ice, and you can see that decline over a several decade period. Many people said, well, that was an anomalous number. That 2007 number was a freak incident. It had to do with wind patterns, all sorts of strange things that were going on that weren't really part of climate change itself. And sure enough, over the next few years, we did not see that record matched. We saw last year numbers came pretty close, but nothing has matched the level of retreat in 2007 until now. If you look at the numbers now, we're well ahead of where 2007 was at this time. I am making a prediction that we will see the 2007 record broken this year. We'll see the least ice ever in the Arctic at the end of the late summer. Okay, all right, so we've seen the evidence, the empirical evidence. Now you might say, okay, well, you know, that tells us changes are taking place. How do we know that those changes really have anything to do with us, to do with the increased greenhouse gas concentrations resulting from fossil fuel burning? Well, there are a number of ways we can attack that question. We can use theoretical climate models, and we can subject them to increasing greenhouse gas concentrations and see if they can reproduce the changes that we're seeing. And again, if you watch those same radio shows or, talk to that cantankerous relative of yours who tells you he heard from so-and-so that this is all a bunch of nonsense and that these climate models are completely untrustworthy, they've never been tested. Well, this is a pretty remarkable test that I'm showing you right here. Okay, this is in 1988. James Hansen, who I understood spoke at this very series not too long ago, made a prediction. In 1988, he did some retrospective analyses. The different colors are different model simulations, retrospective simulations that he had made of the 20th century. And the red is the actual instrumental temperature record. And you can see that the simulations overall captured the warming evident in the actual record up to that time. But you might say, well, he knew exactly what had happened, and he just tweaked his model to fit the observations. That's what the contrarians might tell you. These modelers, they just tweak their model to fit the observations. Well, as Yogi Berra said, predictions are tough, especially about the future. And that's exactly what James Hansen did. He made a prediction for the next 2 decades. In 1988 through 2020 here, So more than 2 decades into the future, 3 decades into the future, of what would happen under 3 different possible scenarios. The one thing he couldn't predict was what fossil fuel emissions scenario we'll choose to follow. We could have become very enlightened and decreased our greenhouse gas emissions stringently and followed the purple trajectory. We could have just, burned everything in sight and followed the green trajectory, or we could do something in between, the blue trajectory, and that's actually what we did. If you look at the underlying assumptions, the fossil fuel scenario embodied in the blue curve is the one we've more or less followed, and that is more or less the warming that has occurred. That is a 2-decade in advance prediction of warming in advance. I would argue a remarkably successful prediction. Might be a skeptic still. You might say, okay, well that looks pretty good, but what the heck happened here? Hansen really blew it in 1991, 92, 93. And that's true. Jim didn't know in 1988 that Mount Pinatubo would erupt in 1991. And when it did erupt, he knew how much ash it sent into the stratosphere. And the nice thing about this volcanic eruption impact on climate is it takes about 6 months for that ash cloud to spread around the globe in the stratosphere where it starts to have a global cooling effect. So he had some time to run his climate model simulation when that eruption went off and make a prediction before it could be borne out. And he predicted that the climate would cool about 0.5 degree over the next year or so, and that cooling would continue for 2 to 3 years, slowly recovering on a timescale of 2 to 3 years with this climate model. And in fact, that is what happened. So what looks like a flaw in his prediction actually provided another test that the model passed with flying colors. Now this is a 2-decade-old model. The models by today's standards are far more sophisticated than the models that Hansen was using back in the late 1980s, and yet that model itself was able to make what I would argue are 2 impressive predictions that were borne out. And I could bore you with discussions of thousands of pages of the IPCC reports and the peer-reviewed literature describing all sorts of other sorts of validation experiments that climate modelers do. The bottom line is these models are fairly well tested. They passed some important tests. With flying colors, we should take seriously what they have to say. Now, if we do take those models seriously, then we might think we can do some experiments with them and try to address some of these outstanding questions, like again, that same cousin or uncle may say, well, okay, climate change is taking place, but it's all natural. It's all due to nature. Well, we can do that experiment with the model. We can put the natural factors in, the measured changes in solar output over the past couple centuries, and volcanic eruptions, which, as we've already seen, have a cooling effect potentially for several years. And those are the 2 major natural forcing factors in the climate system. And we have measurements of them for decades, in fact centuries. We can put those into the climate model, see what it does. This is a whole bunch of climate model simulations. Keep in mind there's some randomness to the climate system, just like there's randomness to the weather. Not everything is driven by some factor, like solar output or volcanoes. Some of it just has to do with natural oscillations, just like weather comes and goes. El Nino events come and go on their own. There's some noise. There's some natural internal variability in the climate system. And so if you start the climate at some point and you subject it to certain factors like solar output changes or volcanic eruptions, not every simulation will behave exactly the same way. There's some randomness in it. And this shows that random scatter, and we can average over it to get an overall average picture of what should have happened if the climate was responding only to natural factors, solar output changes, and volcanoes. That's the blue curve here. And now I've plotted it on the other side, and I've plotted the instrumental record along with it. So not only can natural factors, as we understand them, as we can best represent them, not explain the observed warming, the climate has warmed in spite of natural factors. Natural factors should have actually been cooling the climate slightly over the past couple of decades. Well, okay, so maybe natural factors of the sort we know can't explain the warming, but that doesn't mean human factors can explain it. Well, actually, we can do that experiment too. We can add in the effect of fossil fuel burning, increasing greenhouse gas concentrations due to human activity, and we can put in the other principal human impact of sulfate aerosols. Industrial activity in industrial regions of the world has put a lot of soot up in the atmosphere. In particular, has put sulfur particles into the atmosphere. These are the same particles that were being produced in the Midwest that led to acid rain in the East Coast. In fact, this area is one of the hardest hit areas from acid rain. That acid rain was because of the sulfuric acid being produced by the sulfate aerosol particles that were being put up into the atmosphere by smokestacks. That had an offsetting cooling impact in some industrial regions. So we have to put that in too. It isn't just the warming impact of greenhouse gases globally, but there's also the regional impact of these sulfate aerosols. Those are the two principal human impacts on the climate. And if we put them into the model along with the natural factors, we do a pretty darn good job in reproducing the observed record. In fact, you can see that cessation of warming from the 1950s through the 1970s. That's because that sulfate aerosol cooling was competing with the greenhouse gas warming. And what did we do in the late 1970s? We passed the Clean Air Act. In the U.S., similar legislation in Europe and other industrial regions of the world. We cleaned up the atmosphere, which was a smart thing to do for many reasons. But what that had was the unintended consequence of unmasking all of that greenhouse warming that had been hidden by this offsetting sulfate aerosol cooling. And we see the warming accelerate since then. I could bore you with lots of details. I could show you that it isn't just the fact that we can explain the surface warming, but the fact is that if it were these natural factors that were at work, like volcanoes, we couldn't explain the vertical pattern of the warming. If the warming were, as many contrarians argue, due to maybe an increase in solar output, as best we can measure solar output, it's actually been decreasing or remained stable for several decades. But maybe those measurements are wrong. Maybe solar output really is increasing. Well, if it were, the atmosphere should have been warming from top down, but that's not what's been happening. The lower atmosphere and surface has been warming as the stratosphere has been cooling. That is the fingerprint of anthropogenic climate change. That is what we predict happens when you increase greenhouse gas concentrations, which in effect warm the lower atmosphere at the expense of cooling the upper atmosphere. Okay, well, you might still say, yeah, I hear everything you've said, but I still think that global warming is the greatest hoax ever perpetrated on the American people. That was actually a statement by a U.S. Senator some years ago, and there are many people who share that sentiment still. Even Newsweek magazine, back in 2007, published a cover article, Global Warming is a Hoax. Well, there is an asterisk there, so maybe we should read what it says. Or so claim well-funded naysayers who still reject the overwhelming evidence of climate change inside the denial machine. There has been a denial machine. There are those who find this message inconvenient, to borrow the terminology of another prominent spokesperson. They have actively fought a campaign essentially against the science of climate change. Back in 2002, there was an infamous memo. It's called the Luntz Memo. It was put out by a Republican pollster, Frank Luntz, who basically coached opponents of climate change legislation on how to use language to try to confuse the public about what the science has to say, to try to convince them that there is much more skepticism within the scientific community than there is, and it even suggested cultivating certain high-profile scientists who could act as advocates for their point of view. And indeed, that strategy, in some sense, has been followed by many. In fact, it dates back even farther. Read books like Climate Cover-Up by James Hogan, Emergence of Gala, a wonderful book by Naomi Oreskes, published last year. It describes this campaign of denial, climate change denial, and how it actually was a natural outgrowth of previous campaigns of denial of the health impacts of tobacco and a whole host of environmental and consumer issues over the past few decades where the science was on a collision course with the interests of powerful vested interests. And climate change is no different. It always happens. I don't know. I never get to actually say what I meant to say. So some of you, in fact most of you, if not all of you, are probably familiar with the most recent episode of the climate change denial campaign. I have been personally at the center of this, the attacks associated with this. Back in December 2009, just coincidentally, a couple of weeks before the most important climate change negotiation in history. I'm sure that was a coincidence. There was a massive leak of emails from a climate research unit in the UK that showed the private correspondences between climate scientists, and these were thousands of emails that were mined and combed over for words and phrases that could be taken out of context to try to make the scientists sound bad, to try to make it sound like the science was being faked, that there was all sorts of supposed misconduct taking place. And the irony in it becoming known as Climategate was that, as we all know, Watergate was about the crime, which was the leak of materials, whereas somehow in the case of this theft of emails from this climate research unit in the UK, it was the victims that were somehow the criminals. It was the scientists whose emails had been stolen who were put at the center of this controversy that became known as Climategate, and it very quickly spread around some of those radio shows that I referred to, and certain networks that are currently being implicated in other similar scandals, theft of proprietary correspondences and materials in the UK. There's some interesting correspondence there. So this became trumpeted around certain sectors of the public discourse, and this became, in some circles, a scandal that was supposed to undermine everything that we understood about climate change. Again, conveniently, a couple weeks before the Copenhagen summit. And Nature was among the first scientific institutions to comment on this, and what they said was that the theft highlights the harassment that denialists inflict on some climate change researchers. I have to say I agree with them on that. And in fact, one of the things that emerged in the discussion was that, this is one of my favorites, that this was, as I myself quoted here saying, those who are advocating action of manufacturing this false controversy to distract the public and to distract policymakers to try to thwart progress in Copenhagen, and they were very effective in that strategy. But as many of my colleagues pointed out, in fact, my favorite cartoon is this one here. Did you see that article online about the global warming emails? Apparently climate change is a hoax. Shut up and paddle. And indeed, as I tell you that, we are now seeing the lowest levels that we've ever seen on this day of Arctic sea ice retreat, which in fact does spell trouble for polar bears that rely on that sea ice environment for hunting. Yeah, or again. So Sarah Palin published an op-ed in the Washington Post just after this Climategate scandal had unfolded, where she said that the emails revealed that leading climate experts deliberately destroyed records, manipulated data to hide the decline in global temperatures. And as soon as I saw that, I contacted the Washington Post and I said, well, I like to think of myself as an expert, and some people actually attributed this line to me, and maybe you'll let me write an op-ed explaining why that's a whole bunch of nonsense. And to their credit, they did. And what I explained in my own op-ed 9 days later was that, in fact, what these scientists were talking about was hiding a decline in bad tree ring data that they didn't want to show on a plot to distract people who would be looking at that plot trying to deduce how temperatures change, when it turns out that for reasons that have been discussed in the scientific literature, these tree ring measurements become compromised in the late 20th century, potentially because of other human impacts like acid rain or ozone depletion. They no longer reliably reflect temperatures, and so they were hiding this bad tree ring data in this nice plot they were producing for a pretty cover of a report. And the irony of this idea that scientists were hiding the decline in global temperatures in an email that was written in 1999, early 1999, was that early 1999 was on the heels of the warmest year that had ever been seen, 1998. And in fact, Sarah Palin's op-ed took place just as the warmest decade ever was coming to completion, and global temperatures in one of the three temperature records that was most maligned in this Climategate attacks was showing the warmest temperature the Earth has ever seen in recorded history. A little bit of a disconnect between the language and claims of those who deny the reality of climate change and what we're actually seeing. And this is just a plot. It shows the number of warm records being broken relative to cold records. So on any given day, somewhere in the US, you can find some place that's probably breaking an all-time cold record for that day. And you can probably find several places that are also breaking an all-time warm record for that day. Records are always broken somewhere. There are enough locations measuring temperatures on a given day that's likely to happen. What you might ask is, well, okay, how often are you breaking warm records relative to cold records? If global warming is happening, we should see more and more warm records being broken relative to cold records. And that's what this ratio is showing you. In the middle of the century, it was about equal. We're now breaking warm records twice as often as cold records in the past decade. And in fact, this month alone in the US, we broke warm records 13 times as often as we broke all-time cold records, the highest we have ever seen for any month in the temperature record. Way off the scales of what's even shown here. So yes, you're that same uncle, or cousin, radio show you're listening to can point to some place that's probably pretty cold on a given day. The question is, on the whole, how often are we seeing record warmth compared to record cold? Are we seeing more and more record warmth over time? And that is, in fact, what we're seeing if you look at all the records. I'm going to try to wrap this up. I've spoken long enough as it is. We can look at projections of the future, how much warming we're likely to see, and you can see there's this whole spread. It depends on uncertainties in the models. The models don't all agree on the strength of those feedback factors that I described. Some models predict more warming than others for a given increase in CO2. And we don't know what trajectory we're going to follow. We could try to freeze CO2 concentrations at current levels. That would be very difficult to do. And maybe we'd end up somewhere in here. Or we could follow with business as usual. And that means that we're pretty much on target to follow the family of red that you see up here. So how much warming that we're likely to see depends to a large extent on what we choose to do in the future. We still very much hold within our hands the ability to determine the future trajectory of global temperatures and climate change. I can show you a movie. I'm not going to do that. I've been talking a lot about temperature changes. Probably more significant for the U.S. and many other regions than temperature changes are the rainfall changes, precipitation changes, and drought. It turns out that if you look at how these models respond to this pattern of warming, you tend to get, for example, more rainfall in the deep tropics because the atmosphere is warmer, it can hold more moisture, but the dry desert belts of the subtropics where you have descending air actually expand towards the poles. So all those dry subtropical desert regions that we think of as being 30 degrees latitude, 35 degrees latitude, they start moving up to 40 degrees latitude, 45 degrees latitude. That's where we are. Okay, tipping points. Not everything is likely to evolve smoothly in response to the warming. There are certain components in the climate system that are what we call nonlinear. A little bit of push, and you push them off a cliff. Okay, and some of those components are the melting of the ice sheets. Because of some of those feedbacks that I've talked about, you start melting the ice. Greenland starts absorbing more of the solar radiation. It warms up even more. It melts the ice faster. You set in motion this sequence of positive feedbacks, which can cause a rapid loss of a continental ice sheet. Once you start putting that retreat in motion through, you put enough warming into the system. And we don't know that we're not already close to that point with the Greenland ice sheet and potentially a large part of the Antarctic ice sheet. Enough ice to give us eventually more than 20 to 30 feet of global sea level rise. That's Manhattan sort of inundating levels of sea level rise. I talked about sea ice. Arctic sea ice is retreating. So these are the IPCC scenarios. You see all these dashed curves? These are what those IPCC models told us a decade ago. This was the most rapid we could possibly see Arctic sea ice retreat, according to the IPCC. And yet, we're there already. You often hear the claim that IPCC is an alarmist organization. Those scientific projections are alarmist. They're overestimating the problem. If you actually take a sober look at the IPCC projections and what's actually unfolded over time, what you find is that the IPCC projections, by design, these are consensus reports, they have to be agreed upon by thousands of scientists, are overly conservative in nature. And in many respects, we've been underestimating the rate at which some of the changes that we're seeing are taking place. The impacts. Okay, well, you all know what that is. Anyone? Four horsemen of the apocalypse. What are they? War, national security, potentially threatened by, if we have no Arctic sea ice in the summer, that means that submarines can and naval warships can circumnavigate the Arctic. Suddenly nations have to think about defending a whole new coastline. And people like Rear Admiral Titley, who's the Navy's official oceanographer, are spending most of their time right now thinking about how the Navy would respond to a situation like that. And of course, as climate change stresses water resources and food resources, which is what the projections hold, you see large decreases in agricultural productivity over a large part of the tropics, where people are already struggling to meet food needs, and you see a large decrease in many of those regions in available fresh water. Increased stress for resources leads to increased competition. Increased leads to what's the word I'm looking for? Leads to conflict, right? Conflict. Okay. Famine. I already talked about agricultural productivity, sharp drops in the tropics in particular. We might see increases in the extratropics in parts of North America and Eurasia, but we're doing a pretty good job already meeting our food needs. These regions in here are struggling far more to meet their food needs, and that's where we predict the greatest decreases. So that's national security, that's war, famine, and pestilence and death. Those are the four horsemen of the apocalypse, and they make a very real appearance in very sober projections of climate change impacts. It's not an overstatement to say that they loom in our potential future if we choose to follow the trajectory that we're on. I don't have to tell you about extreme weather and heat waves. We just experienced another near-record heat wave in the U.S. over the past week. It's cooled off somewhat in the Northeast since then, but the models tell us that we're increasingly likely to see this pattern of the subtropical high-pressure zone that we associate with the hot deserts expanding, as I said, forward into mid-latitude regions like the east coast of the U.S., and that's what we're seeing. My colleagues, if they're put on the spot and they're asked, can you blame this event on climate change, will very responsibly tell you, no, we can't explain the fact that this particular heat record was broken on this particular day. We can't say for sure that it was due to climate change, but I can turn around and say that if I'm playing with a loaded die that's loaded to give sixes twice as often as it should, and I clean your clock, and we're betting on the rolls of that die, and you look at it and you say, well, you've loaded it, you erased the 5 and replaced it with a 6. I can point to it and say, you can't prove that any one of those rolls that I won on was due to my loading of the die, and that would be true. But what you could say is statistically, the fact that I lost all my money was due to that loading of the die. And that's a better way to think about how climate change is changing our weather. It's loading the die in favor of these extreme weather events, not just extreme high temperatures. I talked about the fact that a warmer atmosphere holds more water vapor. Water evaporates more readily from the oceans in a warmer world. It means water cycles through the atmosphere more quickly in a warmer world. It means you get more extreme rainfall events, even potentially at the same time that you're seeing more severe drought. Water is just cycling through the atmosphere more quickly. And you get larger rainfalls when they occur, but they may be spaced farther and farther apart. So you can actually see worsened drought, and you can see increases in flooding. There's some evidence that we're already starting to see that sort of impact. Tropical cyclones are projected to become more intense. There's still a fair debate within the scientific community about whether we'll see more Atlantic hurricanes or less of them. That depends on all sorts of complicated things like how the El Nino phenomenon will be influenced by climate change. But what we can say is that the strongest storms will likely get stronger as there's more fuel, the warm ocean surface, to drive these storms. In a warmer climate, sea level rise, I've already talked about that. A picture's worth 1,000 words. Finally, vulnerability and adaptation. Yeah, there's certain things we can do to try to adapt to climate change, moderate amounts of climate change, but the bottom line is that there's nothing that we can do to adapt, given the adaptive capacity we have right now with the population that we have globally. Even a moderate amount of climate change will induce changes that are going to be very difficult to adapt to. Whether it be by damming projects, building coastal defenses. So ultimately that only leaves one possibility. If we believe that 3 degrees, 4 degrees, 5 degrees of warming is unacceptable when we look at the impacts that that warming is likely to have, the only way to deal with that is mitigation. Now, you might imagine that we could get really lucky. We could think of some scheme, from one of those, some diabolical scheme where if we do everything just right, we put these particles in the air and we can get the trees to respond this way, and everything works out just the way that our plans have been working out, we might be able to offset some of the global warming through geoengineering, through modifying the atmosphere or the land surface or the oceans in some other way. But recent events have told us that we're very good at creating problems that we don't know how to get out of. Just over the last year and a half, we've seen technology create a massive oil leak at the bottom of the Gulf of Mexico that we didn't know how to fix. Eventually, we finally fixed it after it had leaked some unknown tons, millions of tons of oil into the Gulf of Mexico. So the idea that technology alone will find some magic bullet through technology to get ourselves out of this problem, I think displays a fair amount of hubris. But there's a lot of discussion about that right now. Serious discussion among scientists that I greatly respect who think that, well, maybe the problem's reached the point we're not going to, gather up the will to confront the real problem of greenhouse gas emissions, so we need to go for some last-ditch effort, some geoengineering effort. I personally don't subscribe to that. I think it's easy to see scenarios where we do stabilize CO2 concentrations below dangerous levels. It's not easy to do. If we want to avoid 2 degrees Celsius, it's about 3.5 degrees Fahrenheit warming of the globe. We probably have to hold CO2 concentrations below 450 parts per million in the atmosphere. And remember, I said next year they're going to be 392. The year after that, 395 maybe. It doesn't take very long until we get 450 if we follow the current trajectory. So needless to say, we have to bring emissions to a peak very quickly and bring them down very quickly if we are going to do that. But it's not too late to do that. It's a matter of finding the will to do it. Some of that we can do ourselves. If you're a Sasquatch when it comes to your carbon footprint, 30 metric tons. For comparison, the average American produces 20 metric tons of CO2 per year. I have a colleague who's an atmospheric scientist who studies elephant communication, which it turns out depends on certain properties of the atmosphere, the lower atmosphere. It allows them to propagate sound signals over great distances. What does that have to do with climate change? Nothing. But in the course of his talk he gave recently, he happened to mention that an average adult male elephant among the group that he was studying weighs about 10 metric tons. So the average American produces 2 adult male elephants of CO2 per year. That's how much the weight of the CO2 that we're putting into the atmosphere per year. So we're pretty much Sasquatches on average. If you want to try to be a Cinderella, say 4 metric tons of CO2 per year, there are all sorts of things that you can do to lower your carbon footprint. And we hear about these all the time, and I don't need to repeat them to you. But ultimately, voluntary measures alone aren't going to do it. We need to put a cost on the damage that carbon is doing to our planet. We have to internalize that cost in the economic decision-making process, whether it's a cap and trade, whether it's a carbon tax. Somehow we have to build into the free market. Nothing wrong with the free market when it includes all of the variables that are important. And one of those variables is the damage we're doing to the planet through our carbon emissions. If the free market is allowed to operate in a way that they don't have to take into account that cost, then it's not going to act to solve this problem. We have to internalize the cost of the damage to the planet into the economic process. And ultimately, we have to pursue both. We have to engage in voluntary measures ourselves that can lower our carbon output, but we have to try to hold our policymakers accountable for putting in place policies that will limit carbon emissions below dangerous levels. And so I will leave it finally on this note. It isn't just an economic issue. Climate change is often discussed in simple cost-benefit economic terms. To me, it's an ethical issue. This is my daughter. And no, I'm not torturing her by putting her underneath a polar bear. At the Pittsburgh Zoo, you can walk through a plexiglass tunnel underneath the feeding tank of the polar bears. And if you happen to be working with Pittsburgh Zoo on a climate change outreach project, you can probably convince them to throw the fish into the pool when your daughter's walking through there. But, I'd like my daughter to grow up in a world where polar bears are still thriving and that she can enjoy, the experience of seeing them and talking about these wonderful animals that exist up in the Arctic with her children and they with their children in the same way that I can today. And to me, that's an intergenerational issue. We can't measure the benefits that we are obtaining today through cheap energy in terms of the costs of my daughter and her generation decades down the road. There's an intergenerational incongruity there. Climate change isn't just an economic cost-benefit analysis problem, it's an ethical problem. I'd like to leave it on that note. Thank you for your patience. I'll be happy to answer questions.
Questions, and there's the first one.
Dr. Mann, thank you for all the work you do. I note that most of your data is IPCC data from 2007. A lot has changed. IPCC data has no methane projections in it. We're a year away from a new report. I assume you're working on it. What can you tell us about what's real today and what we might see in the next report?
Great question. I agree with pretty much everything you said there. And I've actually decided to keep my distance from the IPCC this round. In some circles, believe it or not, I'm a bit of a lightning rod. But I have colleagues who are working closely on that. I have some knowledge of sort of what's going into the next assessment. And you put your finger on one of the critical issues. We are only now, everything I just showed you with those climate change projections, those models are all done under the assumption that CO2 is something we control through our emissions alone. But as the question, as the gentleman alluded to, that isn't quite the way it works. I talk about feedbacks in the climate system. And one of the feedbacks I didn't talk about quite as much are carbon cycle feedbacks. As you warm the climate, we warm parts of the coastal shelves that have methane trapped as in a crystalline form along the bottom of the ocean. With a little bit of warming, that methane can be released and eventually makes its way into the atmosphere. As we melt permafrost in the Arctic, there is quite a bit of methane that's frozen in that permafrost that can be released into the atmosphere. So there is a whole other set of feedbacks I didn't really talk too much about called carbon cycle feedbacks. And we can only think about ways that these amplify the warming. We can't think of any way that carbon cycle feedbacks are going to lessen the warming projections of the models. But we can think of lots of ways that they're likely to enhance the warming. And the fact is that those are simply treated as unknowns. Some of them are known unknowns. Some of them almost certainly are unknown unknowns. And what worries me are not so much the known unknowns, like the methane clap rates and the permafrost methane. It's the unknown unknowns that we haven't even thought about. And it's very unlikely, given past history and the evolution of our understanding, that these sorts of unknowns are likely to work in our favor. They're far more likely to work against our favor. And that's one of the reasons that at every juncture, the IPCC has been overly conservative, whether it's with regard to the melting of the ice sheets, where the IPCC 10 years ago said, we're not going to see the melting of the Greenland and Antarctic ice sheet for at least 40, 50 years. Well, we're seeing it right now. We're measuring it. They are now losing ice. We're not going to see an open Arctic Ocean in the summer until the end of the century. We're on course to see it in a few decades, and the military is already planning for it. And I could go through a whole laundry list of other areas, and methane feedbacks and carbon cycle feedbacks are one very good example where it's easy to envision warming that's much greater than what the models are currently projecting. And as is often the case, as you learn more about the science, sometimes the uncertainty range expands because we learn about things that we didn't know about beforehand. Those are the sorts of things that keep me up at night, are not the things that the models are projecting right now, the things that the models aren't projecting that they ought to.
Yes, over here.
Not all CO2 is created equal, right? I mean, you have trees that are producing CO2. So what is the difference between the natural production of CO2 versus fossil fuels that were causing the big deficit in that?
Yeah, another great question. I mean, CO2 for a very long time was balanced. Atmospheric concentrations were fairly stable. They were changing with the ice ages, but during an interglacial period or a glacial period, they were basically constant for tens of thousands of years at a time. And that's not because there aren't all sorts of fluxes of carbon in the system. It's because there was a balance, the same sort of balance you have in a bathtub that's being filled and it's got a drain and it reaches the drain level and water's coming in but water's going out and it doesn't flood, it stays at the same level. CO2 has sort of worked that same way. There's a balance between CO2 produced by respiration, by animals and plants, CO2 taken in by plants, CO2 that's weathered by long-term weathering processes, and all that stuff is sort of balanced on a long time scale. What we've come in and done is to offset the balance, is we've increased the rate of input into the atmosphere through fossil fuel burning, and there's no counterbalancing sink to take up that CO2. Now, that's not entirely true. We can actually see that the terrestrial biosphere and the marine biosphere have actually absorbed some of the CO2 that we've produced, but not all of it. CO2 in the atmosphere has built up about half as fast as it should have given the input into the atmosphere. And that's because plants, both terrestrial plants and the marine biosphere, have been taking in about half the CO2 that we've been producing. That takes us back to the previous question. What happens if those reservoirs of taking in CO2 are no longer able to act as effective sinks as they have been in the past? If we take away those sinks, then suddenly the airborne fraction of CO2, the CO2 that's actually making it into the atmosphere, builds up twice as fast as it did before. That's actually one of these positive carbon cycle feedbacks that we worry about. There was a paper published in Nature just in the last week that suggests that the terrestrial biosphere is already becoming a weaker sink of CO2 than we had thought. So we're actually seeing those changes take place in real time. Yes?
I'm familiar with your uncle and your cousin, friends of mine. I wonder if they haven't been able to attack the carbon isotope ratio issue. Have you run across any of the deniers who try to go there to offset that caution?
Well, in my sort of hierarchy, I envision different levels of denial. And the sort of lowest level in a Dantean sort of sense is CO2 denial. Is the denial that the CO2 is increasing, or if it is, that it's not natural. And as you point out, there is no reasonable, scientifically plausible argument when faced with the isotopic evidence. So, we've seen that CO2 is increasing. And you might say, well, maybe it's something unusual about the way the terrestrial biosphere is changing its natural nature. But there's actually a fingerprint to that CO2. If it were natural in nature, the carbon would have a certain isotopic ratio, carbon 12 versus carbon 13, the two stable isotopes of carbon. The relative abundance of those isotopes of carbon in natural CO2 is different from the abundance in fossil fuel-based CO2. And sure enough, if you look at the way that ratio is changing, it's changing in an exponential fashion that looks exactly like the CO2 curve itself, and that tells us that increase is coming from fossil fuel burning. So, yeah, you still, every once in a while, in fact, a couple of years ago, I was watching CNN. I was at the AGU our big annual conference, and I was in my hotel room, and they put on the TV, and I saw a congresswoman from Tennessee who was actually expressing CO2 denial on, I think, the Larry King show. And I was actually able to use that in the lecture that I gave the next day as an example that it still exists. CO2 denial, the lowest rung of denial. But mostly climate change deniers have retreated as the evidence has become stronger to sort of, it's not happening, it's happening, it's not due to us. Well, maybe it's due to us, but it's very small, it's not going to really amount to much. And okay, well, it's not that small, but it's going to be good for us. And then finally you come full circle. Well, look, it's already underway, and it's so great that there's nothing we can do about it anyways.
Perhaps one more over here.
Thank you very much for this. I'm a farmer and have been working on regional food security. And I've become much more concerned about what I call weather change that you were alluding to, and climate change, at least in the near future. And, just in the last couple of years, seeing the extremes in temperature in Russia and droughts in China. And this year, while we're flooding the Missouri and Mississippi, the Lake Champlain, we have farmers selling their herds in Oklahoma because of the drought. It seems to me it's much more difficult to make scientific predictions on aberrations than it is on trends. Can you speak to, you mentioned that as the moisture increases, the volatility increases. Will this continue to happen?
That's another great question. So, this is, and it's such an important issue because, it was an increase in like 30%, I think, of food costs over a large part of the world over the past year because of specific weather events that happened at just the wrong time that destroyed food supplies. And it's very difficult to get a climate scientist on record saying that we can relate these events to climate change, not because we can't do it, but because if they say so, they're going to be descended upon by hordes of attackers who will vilify them, and they will, well, I speak from some experience, they will come to regret ever having spoken frankly about the way they see it, the way they actually see it. And so I see many of my colleagues who are so careful with their words that they simply end up understating the degree of connection that we can draw. And one who doesn't fit that pattern, a good friend of mine, a very respected climate scientist, Kevin Trenberth, who's one of the foremost experts. He's at the National Center for Atmospheric Research. He's published dozens of papers on the relationship between atmospheric circulation and weather anomalies. And what he's pointed out, and this is the way I frame it, the wrong answer is that we can't relate any one event. We can't relate this event to climate change. Climate change is present in every weather event. Every weather event that we experience now is a combination of the change in the baseline climate and the random vagaries of weather. So climate change is contributing, in a sense, to every weather event that we see. And you can even go a little bit further than that. The extreme heat and the fires in Russia last summer, Moscow, and then the record rainfall in Pakistan. If you start to look at any one of those events as isolated, you might say, it's a freak event. But when you start to step back and you look at the large-scale planetary waves, the pattern of the jet stream, there is a very special configuration of the jet stream that led to that record heat and drought in one location. There is it's that same sort of anomaly that is responsible for the fact that we've seen record flooding in the upper Midwest and we've seen record drought in Oklahoma and parts of Texas. It isn't that there's drought everywhere, there's flooding everywhere. It's that the atmosphere is stuck in a particular configuration. The jet stream is stuck in a particular configuration for much longer than it ought to be, just due to the random vagaries of weather. Climate change is influencing these, what we call persistent anomalies, these blocking patterns. These high pressure regions tend to sort of sit there and are more stable than they were in the past. And there's some work now suggesting that that can be tied. Some of that can be tied to climate change. So I think there is a connection there. I think we're too quick often to dismiss the connection, and I actually think that 99% of the impacts, as you allude to, are going to be in those connections. The way that climate change is impacting the day-to-day weather. That's really where we're going to see the impacts on agriculture, on water resources.
Thanks. We'll let you have a rest now, but this has been a comprehensive, if not somewhat depressing I want to alert you that August 26th, we have our next public lecture here. Again, it's a Friday night. Dr. Peter Kariba of the Nature Conservancy. Those of you that are members of the Nature Conservancy and get the magazine will find in your recent magazine a picture of Peter standing on a stool writing on a chalkboard about the future of conservation biology. He wants to talk about an environmental vision of the future, as seen through what the Nature Conservancy is trying to do. A well-known character in circles of ecology, and I'm sure that will be an entertaining and instructive evening as well. Once again, many thanks, and many thanks for all of you for coming.